Hi, this is abstract on this paper on cubic Kummer type towers of Garcia, Stichtenoth and Thomas by Maria Chara and myself, Ricardo Toledano. So we begin with some basic definitions. A tower of function fields over a final field fq is just a nested sequence of function fields. We say that the tower is admissible if each extension fi plus 1 over fi is finite, separable, and of degree at least 2. We also ask that fq is algebraically closed in each fi, and that the genus of fi goes to infinity as I goes to infinity. So when we have an admissible tower over fq, we can speak of the genus of the tower, which is just the limit of the genus of f5 divided by the degree of the extensions fi over f0. And if we consider the n of fi the number of rational places of fi, we can speak of the splitting rate of the tower, which is just the limit of the number of rational places of fi divided by the degree of extension fi over f0. An admissible tower will be called good if it has positive splitting rates and finite genus. Otherwise, will be called bad. There is an equivalent way of seeing this, and this involves what is called the limit of the tower, which is just the limit of the number of rational places of fi divided by the genus of fi. If this limit is positive, it can be seen that the tower is good. Otherwise, this means that the limit is 0. The tower is bad. So good towers of function fields over a finite fields are useful in, for instance, coding theory as some related topics. And that is why people, one of the reasons people study good tower of function field over finite fields. So a particular class of towers which are useful, for instance, in coding theory are the ones called recursive towers. So for a recursive tower, you need a sequence of transcendental elements over fq and a polynomial in two variables, f of xy, such that when you evaluate f in xy and xy plus 1 is 0 for all I. In this way, you get f0 just as the rational function field, and f1 is constructed by adding x1 to the rational function field f0, and so on. And we also ask that the degree of fi plus 1 over fi should be the degree in the y variable of the polynomial f. In particular, when the polynomial is of the form y to the m equal to some polynomial in x, and m is coprime to the characteristic of the final field, we are in the presence of the Kummer type tower. And when this polynomial in x is of the form x to the d times g of x, with m and d coprime, the degree of g n minus d, g in 0, not 0, and the main coefficient of g of x is nth power of some element in fq, we say that the tower we get is a tower of Garcia, Stichtenoth and Thomas type, or just GST type tower. In 1997, Garcia, Stichtenoth and Thomas proved that any GST type tower of Q always have positive splitting rate. So it just remains to see when they have finite genus, and they proved that if you can find a finite set S in the algebraic closure of FQ, such that 0 is in S, and for each element alpha in S, all the roots of the polynomial x to the d times g of x equal to alpha to the n are in S, then the tower has finite genus, so it is a good tower over FQ. So obviously the last condition imposes some strong restriction of g of x, and the natural question is, if you have a polynomial x to the d times g of x satisfying the above condition, how this polynomial g of x looks like. So related to this problem, Lenstra in 2002 proved that in the case of a GST tower defined over a prime field, then no finite subset S of the algebraic closure of Fp can be found satisfying the above condition of Garcia, Stichtenoth and Thomas. So actually, we believe that any tower of GST type over a prime field has infinite genus, but so far we have nothing to say about this question. So for our purposes, we need this extension of Lenstra result, and in this case, extension means that we are getting the same result over a final field Fq and not just a prime field. In this case, Q has to be the form P to the R with P congruent to 1 mod M, M different from D in Fp, and M and R coprime. Then, again, we cannot find a finite set S in the algebraic closure of Fq satisfying the condition of Garcia, Stichtenoth and Thomas. So in the particular case of a cubic GST tower, we can prove the following. The power d have to be 1, and this forces the polynomial g of x to be a quadratic polynomial, which must split totally in two different linear factors over Fq. Moreover, if a finite set of the algebraic closure of Q can be found satisfying the condition of Garcia, Stichtenoth and Thomas, then when P is odd, P has to be at least 7, and there are some relations between or among the coefficients of the polynomial g of x. More precisely, the specific form of the polynomial g of s is this one we show here. Here, for instance, the quadratic coefficient is -4 times 1 over phi, and this means that it's the inverse of phi in Fq. So we get this sort of precise answer in the case of P odd, and even more when P is congruent to 1 mod 3, we also have some restriction on the final field. Q has to be of the form P to the 3 times k, where k is a positive integer, and for P has to be of the form t squared plus 243 squared, which is a very strong restriction on the characteristic of the final field, if such a finite set exists. In the case of P equal to 2, we just can say that B squared has to be equal to A times C. Well, from this result we get some interesting corollary, and we are showing just 2 of them. And one of them is a sort of Lenstra result, a specific Lenstra result, saying that if you have a cubic GST tower of Fp to the R, then no finite set in the algebraic closure of Fp can be found satisfying the Garcia, Stichtenoth and Thomas condition if the characteristic is phi or is something congruent to 1 mod 3 with R equal to 3k plus 1 or 3k plus 2. Interestingly, we can say something very precise over F4, that there are exactly 3 good towers of GST type over F4, and we have the specific form of these 3 good GST towers. Well, that's all, and thank you very much for your attention.